Hello, how are you? I hope you're doing good. Welcome to today's study. Having studied the design of a solid RC slab, today we are going to see how you can design such a slab using this British Standard Excel sheet. This is an Excel sheet that has been developed to make work easier, such that you just feed in the parameters and it helps you out with the design. So let's dig in. In one of our videos, we designed this slab, and the link of that video has been provided below. And I hope you remember we went through the steps as they have been listed here. We obtained the moment coefficients from the British Standard, and then we determined cover, and using the loading we were able to get to design for bending moment, and we checked for shear and deflection, and we also did that determination of reinforcement for the long span, and then determined the top reinforcement in our slab, after which we calculated the distribution steel, carried out the crack check, and then sketched our slab. So today we are going to use an Excel sheet to do the process. You realize the manual calculations were very lengthy and tedious. So the first thing, once you have this Excel sheet, you come and write the project title here. You can overwrite this one. So it is a proposed development, or we can say Bromtech, let me use caps, Bromtech proposed slab. So that is our project. For the client is the Bromtech subscriber. Yeah. Then we determine the location. Our slab was a roof slab which was on the second floor. Just like that. Let's delete that. And then in the determination of the location, we also need to determine the location of our grids. It was Fi, and that was the short dimension. So F2I, it was the short dimension. So here you can observe the dimensions fed here. Ly, we said, is the longer dimension. Lx is the shorter dimension. So the shorter dimension is Fi, and then the longer dimension was 47. Therefore we have been able to determine the location of our slab, and that was actually our first step. Let's go back. That was our first step. Secondly is slab classification, and we said Lx is the shorter dimension, Ly is the longer dimension. So Lx being the shorter dimension is 4.25, and then Ly being the longer dimension, it's 4.4. Once you do that, it is okay. But what if I accidentally use a bigger dimension here? Let's say 4.5. You see, it is failing on Lx over is greater than Ly. This is because the program has been programmed. This Excel sheet has been programmed to consider Lx as the shorter dimension. So this is 4.25, and that is 4.4. And once you feed that, it directly classifies your slab. And the next parameter you do is now in terms of determination of this moment coefficient and all that, it is going to do. So our work will be just to feed these blue requirements. So our H, this is the total depth of our slab, was 150. So you can even change it to 200, and then let's still retain our 150 because it is safe. Our cover, when you look at the British code as we studied here, let's get there. Where was cover? Let's go back to determine. Yes, cover, it was 20 millimeters, so you can read your code and feed that value. And then hope you remember h was 150, which we have already fed. The program will calculate the rest. So it is 20 both top and bottom. From there we proceed to loading, and these are the characteristic loads. The self weight, it automatically calculates because of the depth, and it is 3.60. And you can observe when we calculated the self weight of our slab, it's right here, 3.6 kilonewtons per meter squared. And then for finishes, or you put these finishes in additional dead loads. So we have inputted 1.5. Hope you remember there is also another video where we have studied the design, or the how to distribute loading from a water tank to a slab. So since this is a roof slab, if we had a tank, we said you take the height of the tank and then you multiply by 10 to get the loading of the water tank per meter square. So if the height of the tank was 2, multiply by the 10, that will give you 20. Add my extra load for finishes, that is 1.5. So I'm going to do 21.5 at this place if I'm supposed to have a water tank there. And you realize something happens, it fails on deflection. But I think let's maintain first of all 1.5. We just design a normal slab. Then you proceed to determine the external the dead load, the live load, sorry. And the live load is 1.5 as it is given from the code. Hope you realize this sum comes to 5.1, and that is what it has done here. It has done the sum and given us 5.1. For imposed load, it was 1.5 from the code, and you can even change it to 2 depending on the utility of the structure, but in this case it was 1.5. So once you have 1.5 and 1.5 and the self weight, it is able to calculate the design load N. But for it to do that, you have to enter these partial factors that we normally consider, and they are actually in the British standard. They are in close 2.4.3.1 if I'm not wrong. So let's check that. 2.4.3.1. I'm taking time to explain because sometimes people take these Excel sheets and they start designing without knowing what they are designing for. So this is the clause. In ULS design of the whole or any part of a structure, each of the combinations of loading given in table 2.1 should be considered, and the design of cross sections based on the most severe stresses produced. So when you look at the load combinations we have, I have dead and imposed, and earth and water pressure. I have dead and wind, and earth and water pressure. We are not considering wind, our structure is just 2 stories only. Dead and wind and imposed load, and earth and water pressure. This is also not being considered here. So we are going to consider load case 1. The load type, we have 4 different types of load types. The first one is the dead load, which is the permanent action, which we normally use a factor of 1.4. And then for imposed loads, we use a factor of 1.6. When they say adverse, these are for ultimate limit state design. And then for beneficial, this is when you do for serviceability limit state. So we just proceed and carry out, use 1.4 and 1.6. 1.4 for dead loads and 1.6 for live loads. Let's read here. For load combination 1 and 2, the adverse partial factor is applied to any loads that tend to produce a more critical design condition, while the beneficial factor is applied to any loads that tend to produce a less critical design condition at the section considered. Where are we saying this? When you are doing an uplift check, when you are designing for wind for high-rise structures, you assume there are no imposed loads in your structure. That is why this beneficial is 0, so that your structure is as light as possible, and you design it to be able to resist uplift when we don't have any live load in that structure. And for dead loads, because dead loads cannot be done away with, that is why we use 1.0. But if we are using we're designing for gravity loads, we use 1.4 for dead loads and 1.6 for live loads, as we have stated. So going back, this for dead load we use 1.4, for live load we use 1.6, and they sum that up and give us 9.54. So let's compare with what we obtained, 9.54. That means we are on the right track. Since we have fed all these parameters, now we proceed and we determine these others in this side. FCU is the class of concrete, and we use class 25, which we used on the other side too. FY, this is the yield strength of steel, and it is given in this code. It was in table, let me get it, it's in table 3.1. the characteristic strength of my reinforcement, and for high yield steel we use 460. But as we stated in another video, this design may be based on appropriate characteristic strength or a lower value if necessary to reduce deflection or control cracking. Therefore, we are going to use a value of 460. That is a value of 460. And the density of concrete, normal weight concrete, is normally 24. The reason why we say normal weight concrete, remember sometimes we can have lightweight concrete that is produced by lightweight aggregates. Therefore, this density is supposed to reduce in that case, but in this case it's just the normal concrete, so it's 24. We also have these partial safety factors that we normally use, and they are in the code. They are in clause 2.4.4.1. We can go there quickly. 2.4.4.1. There is a table that is supposed to be there right here. 2.4.4.1. in the assessment of the strength of a structure or any of its parts of cross sections, the appropriate gamma m values should be taken from table 2.2. These values are for the ultimate limit state. Look at reinforcement. It has a value of 1.05. So we use 1.05. That is for steel. 0.5. And then for concrete, it is here, concrete in flexure or axial load, 1.5. 1.5, it's correct. But I hope you realized initially here we had 1.15. When you look at this code, this is the 1997 version. I think in 2005 the characteristic strength of reinforcement was revised from 460 to 500, and once it was revised like that, the reinforcement value was also revised from 1.05 to 1.5. So when you're using like the Euro codes, you are going to use 500 as the characteristic strength of reinforcement, and you'll use 1.15 in this case. But since this is the British standard and we are still using the 1997 version, having assumed 460, we will retain this to be 1.05. The reason why the value for steel is less than the value for concrete is because in the production of steel, you can easily control the parameters and control the output that you expect. But for concrete, whenever we are batching concrete on site, there are very many things that can go wrong. You could have water that is not right. You could the contractor might use improper ratios, and sometimes the aggregates are dirty. So there are very many things that could happen. So that is why the factor for concrete is high, so that we ensure safety when we are designing. Having fed all those parameters, now we proceed to the edge conditions. In our slab, we had one long edge continuous and all other edges were discontinuous. So let's pick an edge that is continuous. Ly is the long edge, so Ly is the long dimension, so we use, let's say edge 1 is the one that is continuous. All the other edges are supposed to be discontinuous, as our slab was. And that is how you do it. Edge 1 is continuous, but all other edges are discontinuous. So we have fed all parameters. Here you can input the parameters of the one who has designed this, and input the parameters of the one who is supposed to check. Do the date here, and you can fit these other details right there. So allow me delete this. Sometimes you could come and say our slab is from F to I and 4 to 7. You see, this is not 4 to 7. So F to I, 4 to 7, but it's not really necessary. Though if you want to input the location here, you can see a way of inputting so that somebody can easily identify this slab on your drawing. Therefore, we have fed all parameters, and this has calculated our BS values. Now we can go back to our manual design calculation. BSX was 0.045. Let's check that. No, we can look for it here. Moment coefficients. For the short span, the first one was 0.0602. Let's look for that. It's right here. It is for the continuous edge. For the, that is one short span. Hope you note this is the short span, and these are negative moments at the continuous edge. So this is edge 1, it's continuous, and the moment is 0.060. So it does not have this other decimal place. Let's proceed. For the long span, let's look for that. Let's finish with the short span. At mid span, it is 0.045. 0.045, and this one we read from the code. I hope you remember. If you have not gone through these the video where we're designing a slab, it is provided in the description below. So go through it, see how we design that manually, and obtain these values from the code. And for the long span, it was 0.044. Let's get that, 0.044. Therefore, it means my Excel sheet is working or functioning properly. And the moments were also determined using the formulas there. And this moment was 7.7, this was 7.5, and this was 10.3. So let's look at that. 7.7, 7.5, and 10.3. For the moments, we have 7.7. Let's look for 7.5, 7.5, 10.3, 10.3. It's not so accurate to the second decimal place, but hope you can appreciate how those values come about. For the effective depth, you remember we had an effective depth of 125, and then this was 116. In that video, we had made a mistake, and we used 121 instead of 116. Where is that? And we corrected that in class. It was here. So we were supposed to delete that and use 10. So this could give us 116. And in the video we have made that correction. Yeah, and of course this is going to affect all these other parameters down here, but it's not going to really affect the reinforcement. Once you repeat that, you will realize that 158 at 200 mm is still sufficient. But go through the video, that is when you can appreciate that. So hope you appreciate that. K prime was 0.156, it was the same all through, and our K, we calculated that and we obtained those values: 0.02, 0.22, 0.026. Let's get some of those K values. 0.0207, another one, 0.02. I hope you are appreciating, because our calculation is exactly giving us what is in the Excel sheet. So you can also check that. And this is supposed to be less than this, otherwise you should have compression reinforcement. Our Z lever arm was also that. This has already been multiplied by the D. Remember, Z is either the value you get from the table or 0.95 D. And most of our Z values were 0.95 D. They are the ones you're seeing here. So Z values were also obtained. In terms of reinforcement, hope you remember we obtained 149, around 150, and 199. Let's check that. The first value was 149. Where was that? Right here. This was 149. The second value was 150. Right here, 150. The third value, it was 150 because we used 121. So if you use 116, it's going to be 155. And the third value was 199. You can see 198. So our manual design calculations are also giving us what is here. Therefore, you go ahead and provide the reinforcement. We provided 10 millimeter bars at 200 mm spacing. Sometimes you can even reduce this spacing. And after reducing that, you'll observe to what happened to the area of reinforcement provided. So let's retain that at 200. So this was 8, 8, 8, 8, and then top one was 10. This one is 8 for edge 3. It's still okay. And once we have that, you now have all these other parameters calculated here. Hope you remember we calculated Fs. And we found our values. We also calculated the modification factor, and we found it to be 2.7. So we decided to use 2. This modification factor is the one you multiply with the value in the table, which was 26, but we considered 20, and I explained why. Let's go to the deflection check. It's here. We considered 20 because we assumed since we have discontinuous edges 3, we assumed simply supported, just to be safe. But you could do 26 and change this to continuous, and this will give you 52 millimeters. Therefore, the actual span over D will be less than the limiting span over D, because that is 34, and when you see from this, it's 34. Therefore, it means our design calculations fully coincide with whatever is in this Excel sheet. Also, remember we stated that for our slabs, we are assuming that they are fully restrained on all edges. That means there is no torsion occurring there. And we assume that our torsion still is 8 millimeter bars. And I hope you remember we read the code that these bars are provided up to a dimension of the shorter span, a fifth of the shorter span. And that is where they are provided. But in our slab, when you study the way we normally tie it, this reinforcement that is provided here for the return of the bottom bars, they make the top bars, and then we bind them with reinforcement, the top reinforcement still. So because of those bars and the beams are sufficient enough, therefore there is no torsion that will be experienced at the corners or at the edges, which means we have resisted torsion. That is why I prefer inputting 8mm bars, because we have already provided reinforcement there. And you can see after providing that, you also have support reactions and all these other values for determination. I believe these are for the determination of shear. And you remember we did our calculations and our slab was safe against shear. So it gives us a summary down here that now provide these reinforcements. Top one, use 10mm bars. For this edge you can use 8, but uniformity, top one you can use 10, and then all these other reinforcements are 8mm, and the short span, which is the main reinforcement, is 10mm. After that, it also gives us a summary of all the checks that have been carried. It has checked and Lx is greater than Ly, that is okay. The cover to reinforcement, the cover we provided, it's okay. Singly reinforced, it's okay. And then minimum spacing, it's okay, and maximum spacing is okay. And remember, there are checks we carried out for cracking, so that is where minimum and maximum spacing comes in. And for deflection, we have already checked together and we have seen the values are the same as the ones we obtained, so it's okay in deflection. Therefore our design is a valid design. So we can go ahead now and print this sheet so that we can give it to the draftsman to detail the slab. Therefore that is how you design this slab. And sometimes if you do not know these values from the code, just feed them and then find out whether it's failing, examine why it is failing, why it's asking questions, and issues, areas with issues. But I hope you appreciate that the Excel sheet is going to make our works easier, so that now henceforth we are not going to proceed to carry out these tedious calculations, but we are going to use this Excel sheet to do our calculations. There are also people who do not believe in the use of these sheets because they cannot really tell what was fed at the back end and the formulas used. But you have realized that it is the same formula when this was being made. Is the same formulas that were used in these manual calculations are the ones that have been used in this Excel sheet. Therefore I hope you have learned. We will still do more videos for these Excel sheets. Continue following us, like our page, subscribe to us, and click that notification bell icon so that you are able to receive notifications from us anytime we post a video. So thank you very much, and I hope you have learned, and now you are able to use this Excel sheet to do your design. Thank you very much. And if you've not watched our video where we are designing this lab manually, go and watch it. You can even design it on your own manually so that you appreciate how the code is used, and then come and feed all the parameters here, and you realize that you will notice that they are the same, and therefore you can be using these Excel sheets for your design. Contact us if you want us to design for you something, and also if you want to engage us in any construction business. Thank you very much. May the good Lord bless and keep you. Adios.